The second case is a little bit different. Here we have a set of bispecific antibodies that's been around in the lab for a while. So people have produced and purified them a bunch of times, performed various assays, and now we want to see, really evaluate, okay, across this list of, I have a little list here on the right side, across this list of 18 that we've now been working with, now we need to cut that down. We want to see which of the different VHVL variants in those two positions actually seem to work well together, and all these aspects that are important. So to do this, we actually need to resolve quite a bit of information. So first of all, which batches exist, and what assays have been done on them. And of course, for the antibodies, which of the binders were used in which of these knob in hole position. And if those binders were mutated to fit this format, what was the original clone, where was that clone found, etc. So again, we have quite a bit of digging to do. So what I want to show you is how to do exactly that in our system. So I'm just copying that little list of antibodies. I'm going to go directly to our analysis tool, close that down, and say that, well, I'm now starting with a list of antibodies. So I can just paste that same list in there. It's found these 18 antibodies. So I'm selecting them. And what the system does then is to look through what different batches exist in any form of any of these antibodies. And for those batches, which assays were run. And which of the antibodies were run together in the same assay, and it pieces all this together. So what we see here now is actually a list of assays for different purified purification batches of each antibody. So this is the antibody name here, and then we can see that this is a purification batch. Because in this case, we have a rule that says if you purify an antibody, take that name, add the code name for the target or targets of that antibody, and then give a number. So you can see there's 001, and over here is 002. So there are at least two different batches. Now we might not want to look at all the data here, so we can actually peek into these data sets and see what were assayed. So we might just want to focus on HER2 this time. So we'll add that ELISA. Here we have an EC50. Let's bring that in. We have, over here we have on and off rates. And then for the second batch, we have another HER2 EC50 estimation. So it's actually been done twice on different batches, which could be interesting to look at. So we just give this a name. I'll call it demo. And we can here look at what we actually now brought together here. So there are some gaps because all the antibodies weren't included in all the assay data sets. But we can immediately start making a simple plot, let's say, comparing those two different EC50s from different purification batches. And as it happens, they have kind of a nice correlation here today. But now, if we really look at this now, so we think about what's in this data set. So on every row, we now have an antibody. So we can take a look at one of these. And we see that, yes, they're bispecific. Just like the example I did before, they have two different VHVLs that originated from different clones. We can also see that they've been produced twice, and 3 different purification batches has been registered. And here we can all see, what assays have been run for each of those purification batches. And of course, we can link our way all the way back to the binder against HER2. And for this one, we can see that indeed it's been mutated, and the original clone is over here. And that clone was found in this library, and so on. So we can actually use these relations to add information into our data set. So I have this magical button here called related columns. Here I can just say, well, for every antibody then, add the binder in the whole position into the analysis. And since we saw that these were actually mutated variants, so add also the parent. And for that parent, add which library they were identified in, or animal. And also add which track and round of selections that they originally came from. So I can update my data set. Now, the headers here quickly become quite messy, but so you can clean them up if you want. But that's fine for now. So going back to this plot, I can now quickly just color that by which was the original clone, or what library did that come from, and so on. So yeah, there's a lot more to do there, but in interest of time, I guess I'll have to stop there. And I have a few final slides. So yes. So again, the scientific data backbone, as we call it now, together with these fairly easy to use tools that you saw examples of today, that are really custom made to fit in the context of antibody discovery and development, but also for other types of molecules. And you can actually define your own library designs and get automatic checks that they conform to the design and so on. So it's actually not, it's a lot, of course there's a lot common if you use other types of scaffolds. We have state-of-the-art security, going on the cloud. And we actually use something called event sourcing technology that gives you this complete audit trail of the data. So nothing is ever overwritten, it's just added upon, and we build this great data state from that. So it's a lot like banks actually do, to track all the transactions. And finally, it's actually very fast to get this implemented. And we have a great kind of process of getting started and getting into a validation program of sorts. So that's it. Thank you very much. We have a booth here out number 12. So if you have any further, if you want to look deeper, we have computers where we can actually do live demos. So please pop by, and happy to talk. Thank you.